All right, so this is Mr. Smith here. This is Algebra 2, Section 7.4, Evaluating Logarithms. Okay, and so logarithm, this term is entirely new to us. We've never seen it before, okay, a logarithm. And we'll get on to what it does, but for now there are two graphics here, and I just want to briefly talk through them. And so here I have y equals 10 to the x. And what we're trying to show by this graphic is that these two are inverses of each other. Okay, remember, an inverse should be symmetrical with respect to the line y equals x, and these look like they are. Okay, so somehow, if I have y equals 10 to the x, then this y equals log of x has to undo that. Right? That's what it means to be an inverse. So, for instance, if I use an x value of 2, then 10 squared is 100. And so when I plug in 2 here, it goes to 100. And so to be an inverse, somehow when I plug in log of 100, it's got to go back to 2. Right? That's what it means when we talk about inverses. So the first idea that I want you to conceive of is if I have an exponential function, then its inverse is a logarithmic function. So this idea is logarithms are inverses of exponents. That's going to be an underlying idea as we proceed here. Another thing I want to talk about here, and I'm just going to try to eke out a little space right in here, is if I have 2 to the x power equals 8. 2 to the x power equals 8. Okay, so this would be an exponential equation. Then x should be 3, right? Because 2 cubed is 8. So that should be a problem that's accessible to all of us. But what if I change it slightly and I say 2 to the x power equals 7? Well, now we don't have a way to think about this problem. And this is a problem for a different section. We're not going to cover this in this section, but hopefully it illustrates the idea that we need some algebraic technique to handle a problem like this. We don't have one, we need one, and we can get one. Okay? Now, we do have a graphing approach. Remember, if I graph y equals 2 to the x power, and I graph y equals 7, and find the intersection point of those two graphs, I'll be able to solve this problem using my graphing calculator, and that's well and good, and very useful. Very useful. But we need an algebraic approach, and so we're going to look for one. So, this is the definition of a logarithm. If you have any hope at all of understanding the next 3 sections, it's going to start with memorizing this relationship. So, a logarithm is just another way to rewrite an exponential form problem. A logarithm is just another way to rewrite an exponent, a power. So the logarithm doesn't imply that we do any math. It's not like 2 log 2 is 4 or anything. It's not an operation. It's a notation. Okay. So the first observation, the first fundamental idea is that somehow exponents and logarithms are inverses of each other. The next idea is that a logarithm is just another way to rewrite an exponent. Logarithm means a type of notation, and that's all. Okay. And here's what it means. If I have b to the x power equals y, then I can write that as a logarithm to say log base b. So this b and this b are the same, right? So log base b of y, that's this y here, equals x, the exponent. Okay, and that relationship is going to be fundamental for your understanding. All right. Log base b of y equals x. That's equivalent to b to the x power. That's b to the x power equals y. So let's see this in application. Again, we're not going to do any math. All we're going to do is rewrite these. So these are written as logarithms. We're going to rewrite them as exponents. Okay. So this is log base 2 of 8 equals 3. So this is the base. So 2, this is the exponent to the third power, and it equals 8. Okay. Again, all a logarithm is another way to write an exponent. So here I have log base 2 of 8 equals 3. So 2 to the third power equals 8. That's what this is saying. It's just another way to write it. Let me show you another problem. So here I have 4. So this is log base 4 of 1 equals 0. So I have 4 to the 0th power equals 1. Okay. The next one, this is the base, log base 12 of 12 equals 1. So 12 to the first power, 12 to the first power equals 12. And lastly, I have log base 1/4 of 4 equals negative 1. So this is 1/4 to the negative first power equals 4. I've not done any mathematics. I've done no computation. I've done no calculation. All I've done is rewrite a logarithm in terms of an exponent. They are interchangeable that way. Two key ideas so far. Number one, logarithms, exponents, or inverses. Number two, a logarithm is just a different notation for writing an exponent. Okay. All right, so now we're going to do a small bit of calculations. These are going to be very nice calculations. And to aid us, I'm going to add in here that this is going to equal some number x. All right, but the next observation that's important is that log base 3 of 81 is just a number. Okay? In the same way that the square root of 4 is a number. Square root of 4 is a number. Log base 3 of 81 is a number. And both numbers can be simplified. Right? The square root of 4 equals 2. The square root of log base 3 of 81 can also be simplified. And so we're going to simplify it. And the way we're going to start is by rewriting this as an exponent. So it's going to be 3 to the x power. 3 to the x power equals 81. And now I'm going to try to identify, well, what value does x have to be? So could x be 1? No, 3 to the first power is 3. Could x be 2? No, 3 squared is 9. Could x be 3? No, 3 cubed is 27. Could x be 4? Yes. 3 to the 4th power is 81. Okay? So, log of base 3 of 81 equals, this just equals 4. Just equals 4. It equals a number. Okay? So again, don't freak out. This is just a number. All right, let's do part B. So log base 4 of 1/4. So I'll write that 0.25 is 1/4, and let's say this equals x, just to help us call this out for all of them. All right, so log base 4, that means 4 is going to be our base, x is going to be our exponent, and 0.25 or 1/4 is going to be what this equals. So I need to figure out an x value, 4 to some power, that gives me 1/4. So x has to be -1. X equals -1. Okay. Let me go through the next two examples, all right? And then there will be a few problems for you to try. So 1/4 to the x power equals 256. 1/4 to the x power equals 256. So I know x can't be positive, because if x is positive, it's just going to give me a smaller fraction. So the bigger the x value is, the more positive it is. I'm just going to get a smaller and smaller fraction. That's not what I want. So to flip the fraction, I know my exponent had better be negative. Okay, that's going to flip this fraction and essentially make it 4 now to some power equals 256. So I flip the base by making this a negative exponent, and now the answer is 4. 4 to the 4th power is 256. So 1/4, listen carefully, 1/4 to the negative 4th power. The negative flips the base, and now I get 4 to the 4th power, which is 256. And so that was part C. Part D, 49 to the x power equals 7. Well, 49 to the first power is 49. 49 to the negative first power is 1/49th. How do I get? It's the square root, right? The square root of 49 is 7. How do I write that as a power? It must be our power is 1/2. Okay. So again, log base 49 of 7 just equals the number 1/2. Okay. It's important that you see this. This is just a number. What number is this? It's 1/2. Okay. 3 ideas. Number 1, an exponent and a logarithm are inverses. Number 2, a logarithm is just another way to write an exponent. It's just another notation. And number 3, logarithms are just numbers. So don't freak out too much. All right. Here are 2 problems I'd like you to try. If you're watching the videos at home, I'd like you to pause the video now and work on these problems. If you're in my class, please pause. Well, you don't get to pause. Please work on the problems now. Cool. All right, welcome back. So the first step we want to do is when we consider these problems, we want to rewrite them as exponents. And now we want to solve these exponential equations. And for the time being, these exponential equations will work out quite nicely. Okay, so you should expect pretty nice values here. Again, you can kind of guess and check your way if you're not sure how to get through these values. Okay, there's 2 other ideas I want to cover, and then we'll be finished for the day. So the first is we have 2 different types of logarithms that we use all of the time. One of them is called the common log. It's on the left side of the screen. The other one is the natural log. Okay. So anytime we talk about log of base 10, we don't have to write base 10. Okay, we just know that if I write log with no base, then I'm referring to log base 10. In the same way, if I have log base e, I don't need to write log base e. We just write that as ln. It's called the natural log. It's called the natural log. Okay. This is just a shortcut in notation. This is a shortcut that we use. If you don't like this, initially you don't need to use it. But you'll notice on your calculators there are 2 buttons for logarithms. There's log, which is log base 10, and there is ln, which is log base e. Those are the only 2 log buttons on your calculators. Okay, which means we're going to have to be able to use and be comfortable with these type of logarithms. So for instance, if I put log of 100 and I don't put a base there, it's understood that the base here is 10. So what is log of 100? Remember, this should just be a number. So log of 100 is 2. The reason is because, remember, there's an understood 10 that's right here, and 10 to the 2nd power is 100. 10 to the 2nd power is 100. Okay. Now the good news is, if it's a common log or a natural log, you can just type it into your calculator. So all of your calculators understand if you type log of 100, they'll give you out 2. This is really nice. But your calculators don't understand this. So you can't just type that in and get out 1/2. All right? Your calculators can only use log base 10 or log base e. And when it's log base e, we rewrite it as ln of x. Okay. So these are our two most commonly used logarithms. And lastly, don't get too intimidated here. This slide is trying to show you that these two functions are indeed inverses. So what they do is they say, well, hey, we have g of x, which is log base b of x, and I have f of x, which is b to the x. How do I know if those functions are inverses? I compose them both ways. And when I compose them both ways, I should only get out x both times. It's the only way I can know that two functions indeed are inverses of each other. And so what they're showing you here is that if I compose these two functions, let's look over here. If I take b to the x power, but where the x was, I replace it with the other function, I get back out x. Okay. And this is probably something that's worthwhile to just kind of memorize how this looks. But the idea was, I had b to the x, but where the x was, I replace it with the other function, which is log base b of x, and this somehow just equals x. It's a very, very nice property. Why that is, I need to worry about yet. Just need to know that happens. Okay, so I take b to the logarithm of base b of x, and that wipes everything out, and it just leaves me with x. It's a really nice property. This other guy, I can show you why this works, but I'm going to introduce a property that we'll see in a later section that's going to allow me to show it to you. And in true mathematical fashion, that really ends up being circular logic, but you'll have to forgive me for that. All right, so we have this really nice property that's going to be very useful as we proceed. And it says this: if I have a logarithm with this value here, the argument here has an exponent, then I'm allowed to bring this exponent out front in the form of multiplication. So I can literally just pick it up, and I pull it out front, and this becomes x times log base b of b. Really nice little property. Okay, it says anytime the argument of a logarithm has an exponent, you can just bring the exponent out front in the form of multiplication. Again, I'm unofficially introducing it now, but you will officially see it, I believe, in section 7.5. And the next observation then is, well, what is log of base b of b? What is log base b of b? And so to help you see that, let's talk about log base 4 of 4. So this is literally saying 4 to what power equals 4? 4 to what power equals 4? Well, that, of course, is just 1. If we have log base 7 of 7, well, this is saying 7 to what power is 7? Again, that should be 1. If I have log base 12 of 12, again, this should be 1. If I have log base b of b, I should also just get 1. Okay. So this thing just equals x. Log base b of b is just 1, so x times 1, which of course is just x. Okay. Again, I'm just trying to give you some brief exposure to how logarithms work. At this point, we're going to stop. There's a homework assignment for just this part of section 7.4. Okay, so it's part 1. There are several problems, but they go very quickly. Good luck. Thanks for your attention.